So to finish up section 9.2, I'm on page 594, and you need to get your formula sheet, that one-page, two-sided formula sheet. And now that you've gone through all of these symmetries and all of these cardioids and limasols with and without inner loops, you need to start writing some things down. And so I'll go through what to write down, and then you decide where you're going to put it or what it's going to look like. But the one thing I want to show you up here, we are not going to do a rose. And a rose was the example 10 on the previous page. And the rose down here, you will notice, has 4 petals. The thing that I want you to write down and have on your formula sheet is that I would just ask you a question about a rose graph. You would need to write down, this is the format for a rose equation. Notice it does say A cannot be 0. The good technicalities of a math book. And then what I need you to know are these bottom 2 pieces. Again, n cannot be 0, well, not again, but n cannot be 0, and so we're looking inside at the n. And that's how we're going to know how many petals a rose has. So hear what I'm saying, that you're not going to graph a rose, but I will ask you, how many petals does this rose graph have? And all you got to do is look at the equation and do one of 2 things. If this n, or this n, if it is even, you double it, and that tells you how many petals it will have. The one on the previous page, if you look inside the formula it is a 2. So to know how many petals it will have, I need 2 times 2, and then when we look at the graph, it had 4 petals. But if, when you're looking at the rose equation, if you look at the n, and if the n, now it can't be an odd number of 1, but if it is any other odd number, then the rose has that many petals. So if this is a 3 theta, 3 is odd, it will have 3 petals, etc. I need you to write that somewhere on your formula sheet. We are not doing lemniscates. We are not doing spirals. That's at the bottom. But you will notice at the top of page 500, well, at the bottom of 595, you're going to start to see a summary. I don't know that you want to write any of this on your pages because these are practical. You can work them out, but you make the decision how much you want to try to get on that poor little one-page, two-sided formula sheet. But what I do need you to find room for are these top 3, which are on page 596. There it is. On 596, I would write these things down. I would write these 2, and these 2. I would write down the 6 pieces of information that have the cardioid, the limasol without an inner loop, and for the limasol with an inner loop. I would definitely write those pieces down. You might want to go ahead and pause and go ahead and write down the things for these 3, and also how you find out how many petals are on a rose from its equation. So we're almost done with this chapter, and the things I want to show you are one last piece on page 396 that says sketching quickly. If a polar equation involves only a sine or a cosine, you can quickly obtain its graph by making use of table 7, the periodicity, and a short table. Don't know why that was funny tonight. And so looking at example 13, it says sketch the graph very quickly. And so from here you can start to identify what it's going to be, noticing that the 2's are the same. And when you go up here, which one has the A and the B? Oh, no, the A and the A. So it's going to be a cardioid. And then you can start with just a regular sequence of our thetas. And then you can realize it is going to be a cardioid, and you can graph it from there. So that's a quick way to do it. And you would have homework, and there will be some multiple choice questions that can make this somewhat easy, but you also need to practice calculating the symmetries. The last thing I want to point out in this chapter is up here at the top of page 597. It's a calculus comment. For those of you planning to study calculus, here is a comment about an important role of polar equations is in order. And so it mentions electronic, wow, rectangular coordinates, the equation here, and the graph is a unit circle, and it's not the graph of a function. And I even referenced this earlier when I said we never had x-axis symmetry, because then that violated the vertical line test and trying to see if it is a function. In fact, it takes two functions to get this, the upper part and the lower part. But in polar coordinates, you have the r equal 1 and the graph is the unit circle, and it does define a function. So make note of this, underline it, highlight it. You all are going to pre-cal either this May mini or summer or fall, or some point you're going to be in pre-cal. And it says for each choice of theta, there's only one corresponding value of r, and that's the definition of a function. And since many problems in calculus require the use of functions, the opportunity to express non-functions in rectangular coordinates as functions in polar coordinates becomes extremely useful. And note also that the vertical line test for functions is valid. In other words, it works only for equations in rectangular coordinates. So just put a big old sticky note there, something to remind you as you go into pre-cal. And a quick historical feature, a guy named Jacob Bernoulli. And he just mentioned that he did not become, it talks a little bit about his calculus and rectangular, and this did not become widely used, and even most geometers who use them for describing odd curves. Finally, about the mid-1800s, applied mathematicians realized the tremendous simplification, and I don't know how you're feeling about polar coordinates right now, but it was a tremendous simplification. It made it easier that polar coordinates make possible in the description of objects with circular or cylindrical symmetry. From then on, their use became widespread. So we leave with a thought on Jacob Bernoulli, and we are done with section 9.2.